Okay, I give it another moment. As no one has expressed a strong opinion, we will stick to what I had said in the chat earlier, and I will go through the solution now for this example, because that will take us 15 minutes. So this afternoon, we're going to cover, we'll go through the example on algorithms that people will try over lunch. And I will then go through Eigen. Is a library which offers some functionality which could be equated to NumPy in a loose sense. And then final topic for today will be C++ threads. Don't think anyone else waiting for anyone else to join. Get going. So I quite like this example for algorithms. It's quite nice, and it's kind of it's easy to see that you're going wrong relatively quickly because none of the individual operations are particularly mysterious. It's not really relying on anything really hidden to happen. You're applying a set of algorithms, and it should give you a sensible looking result. The way to do this to not drive yourselves mad is to shove loads of print statements in here, see out, and just run print vector every 5 seconds. Now, some of this is done for you because it's printed at various stages, but you can always add in more of them if you think it's going to be helpful in understanding what you're doing. So if you felt stuck or you got lost, print is your friend, which is not surprising, maybe. Okay, so we're going to work through a number of items. The way this code is run out, so we have our print function, which is available. We'll just print out members of a vector using a range-based for loop, which is pretty standard. Like the first section, we have a bit of a warm-up, some basic algorithmic usage. We have a vector of length 50, which is made up of integers, called nums. We can initialize this with some random numbers. So this is the one area where I think it's quite useful to add print in. Now, is this going to compile without doing anything else? Okay, it's going to print some stuff for us. Sorted nums here, because that's where the first print statement after this definition of nums is. It's not going to have sorted them because it's just going to call the random number function lots, but this is our output. So if we get this little section working, then we should have this as a sorted list. And you can see subsequently when you're looking at different reverse sortings and nums, it's producing the same list because it's just calling print nums. It's not doing any ordering changes, but it's just printing the same thing because we're doing algorithms which output on to the same location as the input. Okay, and the stuff below about Fibonacci sequence as well is available for us later. So the first thing is we generated these using a for loop, but we could have also done this by using an algorithm and a lambda. So just to make sure we can see that there's a change here, I'll do print vec nums here. So we get the print out from this. I probably want to do something like this. Okay. So as a bonus, we can use an algorithm library to generate the random numbers instead. So to do this, as hinted at, we can use the generate and begin num and we're going to get end of num, and we are going to call gen the algorithm. And that will generate us some new random numbers, and we can just do print back to check this. It's changed. Thank you. Before I mess up again, what have I done? Oh yeah, something in my solution has changed. Wait for this. I do that entirely the wrong way. It did. Check this is this. Okay. Yeah. So we hide our mistakes. This definitely isn't being recorded, but now we end up with what we expected. So we managed to generate an initial set of random numbers with our for loop. We've then used the generator function to generate a second set of random numbers to show that we can do it with the algorithms instead. And all the print statements below are copying that second set because it's been generated into the numbers vector. So we expect them to be the same thing being printed later on. Right. So now we've generated the random numbers, we need to sort them. To do that, kind of obviously, we call standard sort. Can also call them in like this. This. Yeah. Good that someone's paying attention. So now we have used the sort algorithm to then get our sorted set of nums. Yeah, isn't? No, it's really valuable, but it's a great way to feel like you're being stupid when you're trying to present stuff to people. Anyway, you now have the sorted list, so a sorted vector of nums produced, and that's what's being printed below because we sorted on number. We've not made a copy in any way. We've updated the vector itself. So the next thing to look at is we've done the sorted, we printed the sorted thing. Now we want to look at reverse ordering. So what we can do here is so again we can use sort. This time we can use change to what we can also pass in a unary predicate here, which is just going to test whether what the order is. So we can use greater, and it's comparing ints in our case, because that's what we've put into the vector we're passing in. But you could see if this was a sort of some member, we could unify this with a single type T, and then everything would flow nicely, opposed to having to put in twice. Okay, obviously this is just an example main function that we're running, but you can see the value in it. Because we've already got sorted this once, we know that if we test the greater than, this should reverse the ordering. Now I check for any obvious errors, which I'm sure somebody can calculate as soon as I do this. Okay, and we run that. So that has reversed the ordering as we expected of the sorted numbers. Okay. Alternatively, we can reverse in a different way. So, okay, you can do two things here. Either you can sort everything back again, which I'm going to do for clarity. Then we can call standard column first. He tries to read it. Okay. So you can either call a function to do this. Copy this so we can see that we've correctly sorted it again before we then different method for reverse. Okay, so we sort back, we reverse again, and we're showing that both algorithmic methods for doing the reverse are equivalent. So we have got safety in the fact that they both did the same thing. Okay, that covers off the first sort of warm-up bit. The main section here now is around the Fibonacci sequence, and this is particularly, I don't want to have in the chat around, this is kind of the bit that trips you up, okay, is this initial offsetting bit. Can people see my screen okay? Because I'm getting a warning that I've got low connectivity before everyone can't see what I'm doing. Jeffrey, are you able to see my screen okay?
Yes, I can see your screen.
Okay, fine. As long as it's fine on your guys' end, that's great. So, so yeah, as we discussed over lunch, this course isn't really around knowing random math sequences. So I'll probably just give this a feature. But I think what it is nice is if you can go look it up and find it, it's important to kind of highlight the initial conditions and these type of things are quite key. And if you make an off by sort of one error in these, then you're going to throw stuff out. And yeah, you do end up with an overflow, and you can fix it in different ways. But the Fibonacci sequence is meant to start with 0 and then 1. Okay. So we can then use. So the aim of this, we're looking to get the first 47 Fibonacci numbers. There's the bonus if we use standard transform. So to do this, we're going to call standard transform on fibs dot begin. I'll just do that again. So this is our input, so we have to give the start and the end of it. Not giving all the way to the end because we are going to run out of space if we do that. So we're only going to go so far. The reason we're going to run out of space is we're running out of space in the output, I think, if this is correct. And then the output is going to be given by, we're going to put it back into this Fibonacci sequence, the vector we call fibs. And the output is going to begin at +1. That's not what I wanted to say. No, sorry. We're going to have two inputs. That's what I mean. To this function that we're going to call at the end. And this was the other overload that we didn't discuss earlier to the transform algorithm, which is +1 and +2. So we're going to go from the beginning at 0 all the way to n minus 2, because we need the next, we need 2 pieces of information to do this and won't be able to go off the end. And then we're going to pass these into standard with a plus operation built in. Again, takes template argument. Again, we call that. And if I've not made any answers, just a second. It's easy for everyone to see what we're doing. Build and run. Okay, and we have a set of Fibonacci sequence. We don't have any minus signs, and this looks like a sensible. I mean, I don't know these all the way up here. I'm sure someone can find an online catalog to verify this if they're really keen, but for our purposes, this will do. But we've generated the Fibonacci numbers, okay? Right, next we want to get all the values that are less than 4 million and store them in fibs less. So this is a new vector that doesn't contain any data yet. We have some condition here that we can fill. So this is going to be standard if, and then we have fibs. Am I doing in the right place? Yeah, fibs dot begin, fibs dot end, okay, which is our input. And then we're going to pass this. We want to use back insertion so that we add these to fibs less. So we're going to pass standard back inserter. So that we can add these onto the end of fibs less. And then finally, we're going to have a lambda function. We only need to pass in, we only need to use it for this comparison, which means we're only going to return, well, we're only going to back insert whenever we have the value of this return true. Okay, right, we're going to copy if this returns true. I'm trying to say. If it does, we're going to back insert. So, to do that, we're going to say x is less than or equal to 4 million. I'm going to say formatting. Okay, and then we're going to close our lambda. We're going to close our call to our copy of statement. That should then fill fibs less. Okay, and now we've got a cutoff at 350 million something. Sorry, 300. Yeah, 300. Yeah, 350 million. That's what I said. And that is given our fibs less output as we wanted to. Right. The next step is we want to look at getting all the evens. So we can now have a new vector evens, which we're going to copy, basically do the same again. Okay, so we know what the pattern now looks like. So fibs less now we're copying from, that's the thing we're going to iterate over. And we are going to again use standard back evens, and then we need another lambda function. But you can see we don't need these functions for anything else than this section of code, so there's no need to run a whole separate function. And this just needs to return a Boolean value, so there's not divisible by, have a remainder, then we don't want that. We want when we do have a remainder, so that should close our diffs. Okay. Run. Now we have even values for evens. Okay, and then our final step is we want the sum. So we just do int sum and look at the standard accumulate. You can also see how if you want to take fractions of this, you don't have to take the full vector, you can take regions if you need to. So just change where you start and end. That should be everything. Okay, and we end up with the sum of all the even Fibonacci sequence. Okay, that's that example kind of start to finish. It's quite nice. It builds on things. None of the operations you're doing are particularly complex. So if you think you've made a mistake or you're getting the wrong answer, you can print out the previous step or the current step and think about certain elements. Once you generate the Fibonacci sequences, you're doing the same thing again. Knowing how to generate the Fibonacci sequence is probably the trickiest bit there, but it's a good demonstration how you can form operations on a containerized set of things. Right. Any questions with that before we move on? Okay. So, given that we've now done we've done templates, we've done algorithms, we're now going to start looking at linear algebra, which is everyone's favorite subject, of course. So what we'll do is we will do the exercise for this is a bit involved. So my plan here is to run these sort of 30-ish slides up until about quarter to 20 past 1, then give you guys about 30-40 minutes to go through all this, and then we'll take a coffee break. And when we come back, we'll go through in detail the answer for this. There's less of a defined solution. It's more about you getting familiar with the setup of these. So let me just get to the notes because I went through some of the examples yesterday so that I have it available. Right. I think that's everything I need. So, the original source of this is Rupert Nash has contributed to many of the slides you've seen, pretty much all of them. But Chris Richardson from Cambridge contributed to this particular section. Okay, so C++ linear algebra libraries, what and why? So eigen3 is what we're going to look at. We're going to talk about how you get started. We're going to talk about matrices and their many forms, dense, sparse, and geometry. We're going to talk about solvers for dense and sparse matrices and iterative solvers. We'll then look at some other general notes, and we'll talk about at the end an example of a diffusion equation demo exercise, okay? Which is going to I will demo we'll look through the demo for the dense case, and then you guys will look at the sparse case. And it will require a little bit of thinking, a little bit of reading through the Eigen documentation. But this is actually quite a nice example because we're going beyond the standard library now, and we're looking at another package and how that integrates with the existing functionality and how you can find useful information on Eigen. Eigen's quite well documented. It's quite nice, and I would recommend it. So do keep this in your back pocket if you need to use it for dense linear algebra. So what do we need linear algebra for in scientific computing, PDE, simulation, finance, graphics, machine learning, and many, many more. What do we expect from a linear algebra library? We expect vectors, matrices, operations between matrices, so matrix-matrix multiplication, transpose, geometric rotation, all the fun things that you usually expect from linear algebra, and additionally solvers for eigenvalues or factorizations or things like CG, things like this. We also expect some types as well to come with this as well, for sort of standard linear algebra type operations. Why use a library? It's simple to use. We've been using a library. We're using the standard template library, but this is a third-party library. If it's a library that is well used and well adopted, other people will look at doing performance optimizations that you don't have to. You do not need to reinvent the wheel every time you come to start a piece of code. You should be using libraries in sensible amounts throughout your own code to improve your sort of code reuse. Otherwise, everyone comes with a bespoke implementation. Some of them optimal, some of them aren't. You probably don't have time to optimize them, and it's a duplication of effort. Okay. Libraries usually have relatively good performance if they're scaled, because if they get adopted, then vendors and compiler people start to optimize for them. They will test correctness for you. They'll be hopefully expressive enough to be able to encapsulate what you want to express with them. They're quite useful, and you just call via some form of clean API. So some examples of linear algebra in C++. We're going to discuss eigen because it's relatively simple to look at, but there are many others. So here are a few examples. So PETSI is quite well used, it's quite popular, and covers quite a lot of stuff. It has its own idiosyncrasies. It does allow you to do some things with MPI as well. And there's another thing to look at if you're interested, but I think it's C-based. You have your standard LARPAC, LARPAC++, ScalaPack libraries for linear algebra as well. These have been around for a very long time, are very well supported and very well optimized for. So these are things you should take a look at, even if you don't have tons of time to look at various libraries. You should not be reproducing these yourself. These type of functions have been looked at heavily. You often find, so in the example for GPU, you have cuBLAS, cuSparse, cuSolve, or RockBLAS, RockSparse, and RockSolve for NVIDIA or AMD. But they will also have versions of the ScalaPack libraries and so on and so forth optimized for their own hardware. So for CPU, that's like Intel Math Kernel Library, MKL, or OpenBLAS, have communities behind them, companies behind them, which optimize for you, which means if you're using them on a particular piece of hardware, we're likely to get the best performance from them for that hardware. But ideally, the API should be interchangeable between what implementation of the library you use, and that would allow you to optimize if you port between hardware. There's some features coming to the future C++26 standard library, but they're experimental. I think that NVIDIA NVC++ compiler, which is not to be confused with their CUDA compiler NVCC. They love to just call everything NV and title everyone else around the bend. They also have a library that they support called CUDA with a Q, which is for quantum cryptodynamics, which is so similar to CUDA in both in pronunciation. It's just brilliant. So they have some of the features already implemented in that NVC++ compiler that you can try out, and they obviously look at the standard pages for C++ to see what's coming. And the idea is to include more of this into the standard template library because it's become so ubiquitous. This is kind of versus what you'd expect in Python is these type of things to look like NumPy, SciPy features. To be honest, a lot of the time, NumPy and SciPy are all they're doing underneath is calling some of these routines, usually in Fortran for NumPy, for example, actually. that are compiled versions which NumPy can then use. It's surprising how much actual compiled code is hidden under Python. Okay. So there's a nice link on the creference.com of C++ links to libraries. It gives you a list of interesting, useful libraries, and there's also a Wikipedia entry for comparison of linear algebra libraries. Also useful just to get a sense of the landscape. It can be quite hard setting out on these things to understand what the community view is of these things. I think the danger is just thinking you've got to work out what the best thing ever is before you start, and that's almost impossible. Try to come to some sensible understanding of your purpose and then pick one and then stick with it. Okay. So eigen3 is what we're going to focus on today in this session. It's a little bit, I don't know if I agree with Joseph's description of this as NumPy, but for C++. It's a header only. So there's no library to link to. So you just pass -i and then the path to eigen to include it in your program. Contains optimizations for ARM and Intel processors, and includes some vectorization for SIMD instructions. Those don't know SIMD, that's single instruction, multiple data optimization for CPUs. It's a relatively easy to use interface, and treats things as if they are sort of the obvious maths objects you're expecting to use, and you might have written down as equations, which makes it quite nice to program if you're coming from a more mathsy background. It supports for dense and sparse matrix, vector, and arrays. So it has support for dense and sparse matrices, vectors, and arrays. So in this case, arrays are not a separate type, but in eigenspeak, arrays are coefficient-wise operations. But you don't need to specify the individual, you don't need to loop over them. By specifying that you're interested in the arrays, it will work out to make sure that the size of two vectors you're adding are both the same length in the addition operation overload for their types. So it's doing a lot of checking for you underneath the hood, which is quite nice. And there's support for sum solvers. There's not going to be everything. You can download this from this link, and you can have to install it into your local environment if you so wish. However, it's easy enough just to download from their GitHub as well, and then have a path to it. So the basics is we have this example. So I've decided to spend a little bit more time on this section, because I think it's quite useful to see some of these things and just show an example piece of text. So this is this example. Here, right. File this. Directory above, I have downloaded eigen. Okay. This was from Git. Got it? Yeah. Okay, so it's just this is the GitLab address that you can get eigen from, but you can search their website and quite easily get it. And in here, there's a bunch of files. You don't need to build anything, in fact. If you just look in, so commonly when you download these packages, if you're not used to this, you'll have an install file as usually the text go to expand it or readme. So again, it just explains eigen consists of a single header file. Hence, there's nothing to compile before you can use it. Moreover, the header files do not depend on your platform, therefore they're the same for everyone. So you just need to include them. Okay, you can do an install, but all that's effectively doing is copying them into a shared location and making sure paths are set and so forth. For us, we're going to do a bit more explicitly. But the key point here is inside this repository, we have the eigen directory, and this has a bunch of eigen-specific functionality. So if we have eigen-dense is a a header file. So include a bunch of other things. Okay. And there's a tree here, and it'll include everything you need for a particular set of functions. So if we go back to the example, yes. Basics.cpp, which is the same we had on the slide. In eigen, so we're calling eigen dense. I'm going to grab an IOStream as well. We're going to have an eigen-typed object of a matrix, which is going to be, the elements are going to be doubles. And again, we're using this ability in C++ to pass integers in as template arguments. So therefore, A is now a 10 by 10 matrix. We're going to set A to 0, and then we're going to pass in a single element as 1.234 in a particular location, and then we're going to print it. Okay, and then but to build it, I just need to do G++ is put -I up to where eigen is, which for me is just the directory above, and then I'm going to compile this. No, it won't. It'll actually work. So you can see what it's also done is eigen has overloaded the operations for output streams, so that it prints in a nice format as well. Oh, because otherwise you'd have to write a separate functionality to print every element like that to do with vector, which doesn't have this type of nice printing mechanism. Okay, and we can see that a single element has been updated in column 0 and row number 9. Okay. So, and this is pretty similar to having a double of C of size 10 and 10. But there's additional functionality which you can run and it makes it more advantageous, like setting everything to 0 automatically. There's a bunch of other functions like that. Okay, the other thing that's important is that example offers something like the array functionality we have in C++, but in a multi-dimensional context. We can also get something that gives us a similar vector-like functionality, where we can dynamically decide the size of our matrix at runtime. While we need to initialize our matrix with some size to start with, we can resize this during operation and then print the new size. So in here, I've got both. In this example, I'm calling dense again from eigen. This is the example we had above, and then I've got a separate section which basically copies the code here in the above, in the previous, in the slide we just looked at. Except I'm calling it B instead, so it's clear what is what. And even though that we've defined initially that the size of this is going to be 64 by 65, we've resized in this size as 20 by 20. That's planned. There is also a bunch of convenience types in eigen. And what these do, so should I find my example of this? Because I wrote one. So what this does is gives you a bunch of types that you can call on, which with some predefined dimensions, so common things. So 3 by 3 matrices are pretty common, or 2 by 2 matrices are pretty common objects if you're dealing with 2-dimensional objects, 3-dimensional objects, or 4-dimensional objects, because those are quite common in physics and mathematics. And you also have a bunch of these with a particular type. So at the top here, in the example, you can take matrix NT to be a matrix of size n of type T, and then you can use the lookup. So you'd expect a matrix 2 I to be a 2 by 2 matrix of integers, or you could have matrix 3F to be a 3 by 3 matrix of floats. Okay. You can obviously define your own, but these are some built-ins in Eigen. You also have the concept of something that is dynamic, and that's just an X is passed in instead, indicate there's dynamic sizing. You still need to pass something to the constructor when you try and make objects of this type, but at least there's a shorthand, so you're not having to write out the full type of information every single time. So, and I think one thing I should stress here, this sort of thing is best just to play around with, okay, to really get a sense of these libraries. Just think of little things, even if it's as simple as testing the dynamic thing actually is dynamic, and then printing the result before and after you do resize. Just checking how it works. It takes 2 seconds to write a 5-line piece of code, and you can test you have an understanding of this. It's quite a nice little set of examples to do. Okay, so now I've got an example here where I've got our previous examples and I've got some an additional pair. So we had our fixed size matrix A, where we passed in the double and the size explicitly. We had a dynamically sized matrix B, where we passed in the size dynamically from the constructor, and then we resized it. We also have a shorthand for this for a fixed size, which says I want an eigenmatrix, which is a fixed size matrix, which is 3 by 3, and it's made up of doubles. Okay, and I can and this is going to be called C, and I'm going to print this. And then finally, I have a shorthand for a dynamically sized matrix, which we call eigen : matrix X, and it's going to be filled with doubles. That's the D. And this is going to be called capital D. I'm going to pass my initial size again, which is going to be 64 and 65. I'm going to resize this to something different, and then I'm going to print out the size again. Okay. Like test, you can see we have what we had before in this matrix A. We have the size as we had in matrix B before. We have a new 3 by 3 matrix being printed out with the example given here, and we have the new size, dynamically sized matrix D being printed. Okay, so it's good to know about these shorthands. They can make our life easier. I'm having a quick notation which to define this. It also gives us, makes our code more readable. But there's lots of options here, just get familiar with them. Okay. In this library is the arithmetic operations that it's going to do for us. Okay. So in this little example, we have here, we have a dynamically sized matrix A, which is of size 5 and 10. We have a dynamically sized matrix B, 10 and 2. And we have a vector of length 10. And then Eigen is going to here say, well, give me the product of these two matrices is going to give me a new matrix C, which is going to be 5 by 2. Okay, so if you multiply these together, the 10 is to be the interface, and then you're going to have a 5 by 2 matrix as a result, which is C. You could also have a new vector based on multiplying A by 10, and that resultant vector W should be length 5. But the key point here is that in the library, the overloading of the operator, the star, the multiplication operator, has been done for you so that it acts correctly for vector matrix multiplication. And this is not available to you in the standard library at the moment when you multiply vectors together. It doesn't know how to vector multiplication, you'd have to implement something. So instead of implementing your own, why not use eigen to do it for you? And with a single header file inclusion, you have a bunch of functionality you can use. Otherwise, you're going to be up to writing a new vector type, a new vector class for yourself to include this. We're trying to add on stuff to the standard template one, which you wouldn't really want to do if you can help it. Okay, and what other type of operations do we have below? We have dot products of vectors. We have cross products, so and we have transposes. We can set things to zeros. We can set things to ones, set regions to ones. We can set things to constant values, and we can set things to random numbers. Again, this is very simple to write a 5-line piece of code to do a bit of testing yourself and understand this a bit better. So that's what I've done, just to give a little bit of an example. Again, I'm starting with the same base. I have an eigenmatrix of doubles, which is 10 by 10, called A, and I'm going to print this in the same way as I've done for the last few exercises. I'm also going to have an eigenvector, which is dynamically sized, of doubles. That's the D. Call it vec, and make it size 10. I'm going to set this to 1. And then I am going to do matrix vector multiplication and get a result out. And I'm going to print W. I am then going to print the transpose of A. Okay, and the transpose functionality shifts rows to columns and columns to rows, if you're aware of that. Okay. So I run /test, I get several printouts. So I get initially what we've always had is the printout of A. I then have a printout of W, the result of the vector matrix product. And then I have a printout of the transpose of A. Okay. These are all very simple things to think about, but they're quite useful to just be able to call upon, because these are very standard operations, and you may well need them when you're trying to implement some algorithm yourself. Okay, element-wise operations. So this is where we can generate quite a lot of confusion quite quickly, because we're going to use the same word, array, that we would do in an entirely different context when we're talking about the standard template library. Here it's a function call on a eigen type. So here we are saying that we're going to generate 2 matrices, A and B, and they are 3 by 3 matrices of doubles. And you're going to fill them to have all. You're going the third line, the one after the comment. We're going to fill A with 2, the floating point 2. We're able to do that and set all the values to 2 because we've called dot array, and that means that all the elements are set to 2. And this is done with some overloading internally, probably. And then in the second block, we're saying we're going to set the elements of A to the sign function of the elements of B. Okay, so again, we have access to sort of trigonometric functions in this library as well. And then the third example here is just giving you a warning that we cannot mix three-dimensional array types with matrix types. This function call of array is different from a three-dimensional array W that eigen also has. So just be careful that just because they have the same name doesn't mean that they're the same thing. Okay, so and I have a brief example of this to show, just to try and make it, just make sure it's clear. So again, I've basically done what's suggested in the example. What all I've done here is I've set A, put all the elements in and printed it. I've set B to ones and I've printed it. And then I've set A equal to the sign of B. So the elements of A are now all equal to the sign of 1. And I've printed that new version of A. Okay. If we run test, so I've got A is a 3 by 3 matrix. B is a 3 by 3 matrix. I've set it all to 2. I've set B will be equal to 1, and I've set new A to be the sign, the elements of A to be the sign of the elements of B, and that's what's going into our final book being printed. Okay. So I'm saying, I know I'm taking my time with this. I think it's worth going through the examples a bit more detailed, Eigen, because it's not part of the standard library, but it does give you a lot of powerful tools to be able to do useful calculations and write them quickly. Okay, so you want to also have the functionality to view other data. So you can mix and match standard vector any of the contiguous layout. It's easy to kind of overlay the existing memory with an eigenarray or eigenmatrix. So in this example here, I've got some standard vector of doubles, little a, which is 1,000 elements, and I'm going to map. I'm going to do a mapping to an eigenmatrix of doubles, which is 100 by 10, and call this A underscore eigen, but it's going to map to the underlying data inside the vector A. We're then going to set them all equal to, some of the elements equal to 1. Also apply this to two-dimensional objects and things like this. So there's lots of ways you can re-represent existing data in an eigen format to manipulate it, basically. So this means you don't have to necessarily rewrite all of your code. You might just be able to manipulate part of it using eigen if that's particularly valuable to you, but still leave it in a representation vector. Okay. The other thing to talk about here is sparse matrices. So a sparse matrix is a matrix which can be quite large and make it a number of zeros. This is quite common for when you're looking at differential equations, where you're usually transforming some form of derivative into some nearest neighbor difference, which means you care about the local neighbors, but then maybe not so much the long interactions between particles, which makes their sites, the interaction between those sites, 0. There is a sparse matrix supporting eigen, which you can call upon to define matrices with various types and sizes, and you can look at row major or column major, I think, as well, in terms of defining the ordering of the matrices. I think it's best to start. I've not got an example for this because it's printing out a bunch of blanks at this point. But for people who are interested in sparse matrix manipulation, there is support there in eigen for that. Okay, right. This bit's important for the example I'm going to ask you to do later. So, in sparse matrices, the easiest way to make a sparse matrix is to build what's called a triplet. Okay, so we're going to have a type def to call triplet a triplet of doubles t. So we're going to make a vector. And see, this is the example. We really have when you call this a list, because now it sounds like the object type is a list, but it's not. So you can have a standard vector of triplet doubles using the type def to do the translation. And on this list of this triplet list, we're going to reverse the elements, and then we're going to push back triplet type. So this is the location, I and j, and the value at I and j that we're going to push back onto this list. Okay. We then have a sparse matrix that we're going to set up with that's going to be empty, and then we're going to set values in the sparse matrix. Oh, sorry, I'm misreading. You're going to reserve the space. Yes. I'm being slow. Sorry, it's okay. For the confusion. You're going to reserve the space. And then you are going to set the values of the matrix based on this vector of triplets. And the triplets basically saying, go through my sparse matrix, find the positions I, j, and put the value in the sparse large matrix of that value. Okay? That is very valuable if you're only expecting to fill a subset of elements, and it gives you a way of cycling through a list to fill. Okay? That's going to be, hint, hint, very useful in the exercise at the end of this example. You also have operators like sparse matrix transpose and sparse matrix adjoint, which can be very useful if you're looking at things like decompositions and you want to write your own algorithms or solvers. They often have these type of operations, joints and transposes, and Hermitian operations on them. They want to be checking their emission and things like this. You can also do sparse matrix addition, multiplication. You can have sparse matrix and dense matrix operations as well. But these are all supported within Eigen. Again, go look up the particular cases that you maybe need for your use case. I won't go into too much more detail here. Okay, you also have some geometry operations. You can do rotations in degrees of a particular setup in Eigen, so a particular matrix or vector or something. So again, I won't go into too much detail, but these are another piece of functionality which is available for you. Right, solvers. That's the next kind of the key thing here. So solvers allow us to solve a system of equations for some result. In this case, we're looking for x. Given that we have a matrix A and a vector B. These are obviously quite common when trying to calculate matrix inverses or things like this numerically. There's lots of types of solvers. We're not going to go into any detail on the particular type that we're going to use, or why we do certain sets of preconditioning to set them up, or why we use a different way to decompose the matrix we're trying to solve because it's more efficient. That's for a separate course dedicated on this. It's not something we necessarily cover, but the point here is that we can, in Eigen, we have a set of solvers that we can call on and decompositions we can choose that are built in that act on their existing typeset in Eigen. So in this example, we've got a matrix, a 3x3 matrix of floats, A, and we've got a vector of length 3 of floats, B. And we're just pushing back values onto these. So we've got A and B defined there in the middle lines. And we're just going to print that out. And then we're going to say, I want the solution to this, which is a vector of length 3 of floats X. And I'm going to perform a solve on this matrix with the input B going into the solver. And I'm going to print the solution. Okay, so that's what I've got in this code here. I'm just copied it off the slide. I would encourage you to go through and do these things as you review this material, if you have spare time to do that. And then I can just run this, and this is calculated the solution X based on the input matrix A and the vector B we provided. And this is the solution to that system of equations. Okay. So key point here is to highlight that solvers are built into Eigen, or at least some are, and you can use them for various situations. Decompositions, there's a variety of decompositions. Again, I'm not going to go into the details of particular decompositions or why you'd use them, but there are a set available. You can look up the documentation. The Eigen documentation is quite nice. It's quite nicely laid out. There's lots of details about how to get started with download and what you want to look into, and a good explanation of what it's actually doing, opposed to just here's a function call. Okay. Other solvers, Jacobi, single value equalization, and then you have eigensolvers, eigenvalue and eigenvector solvers, and sparse solvers as well. Okay. Again, you can have iterative solvers, so CG, least squares, conjugate gradient, and by CG stab. You can use with a precondition also. So these are stored in the linear, iterative linear solvers. Also, again, explore in your own time. I will not go into too much detail here, apart from just calling the solver. It's more to highlight that the library contains them for you more than anything. Some general notes. Eigen does a lot of checks in debug mode, so turn on optimizations 02, etc., and turn off debug. Otherwise, you may not get the most optimal performance from the library. I think that's what this is hinting at. So just be careful of that you do this. Otherwise, you may see slightly slower performance than you might be able to achieve. You can use external BLAS LARPAC libraries that are optimized for a particular that you particularly want to use, or might be optimized for particular hardware you have access to, or for certain functionalities by calling eigenuse BLAS. By enabling the macro eigenuse BLAS and then setting the BLAS library that you use. So it allows you to interface with other libraries as well in Eigen itself. Again, you need to test performance for your particular case, opposed to blindly trusting that one of these is better. MKL, for example, is not going to work as well on AMD hardware because of certain choices Intel have made. Give you an option if you think there is going to be an improvement. Right. So I wanted to give a bit extra time for this, and I think if we've got probably half an hour or so now, at least to go through this example. I think the way we're going to do it is I'm going to kind of leave you to look at both the explicit, implicit, and the final exercise here in the notes, and the last exercise is sparse. You should be able, I would set these up and run them in separate directories. So I would, no, I think they are given separate names in the output, but basically they're going to run a simple solver. And they are going to solve this equation that the rate of change of t in time is equal to some constant and the second order differential of t in position and space. So in 1D, you can use an explicit method for this, and you can take each time step can be iterated by saying t, the next time step, t of n plus 1 is equal to a matrix, times t of n. So we can then therefore create an initial vector for t, and we can create a dense matrix for a, and matrix multiply a several times in order to calculate the future state. And some examples that you can see the example of the exercise explicit.cpp. What this actually looks like in the implementation is the following. So remember, on the right hand side we have the second order differential of in space, and on the right we have the first order differential in time. So if we move everything to the right hand side, so these are at the same time here, but if we move everything to the right, I can say that the next time is equal to, the next state of the iteration is equal to the existing one plus our factor and some overall constant in front in terms of our step sizes, and k times the differences in the current state of our system. And if we take k delta t over delta x squared to be little delta, our matrix A looks something like this, which is just some relatively, which is just some matrix. I wouldn't say this is necessarily relatively sparse, but it's just some matrix involving deltas. And all this is saying is that the position of this in here is based on the location of these I+1 i's or I-1's. Alternatively, you can phrase this. So, okay, and here's the example of the code. And there's a full example in the repository to try. And the focus of this exercise is going to be, of this explicit exercise is going to be to try and just run the code and see what comes out, and try to understand it. And then there is one you've got to try and write yourself. You're going to take delta to be 0.4. This is just some arbitrary input that makes it look nice. And then for every n in terms of the size of the problem space, n, not the number of steps we're going to do to iterate, we are going to add in to A our deltas. So initially we said we're going to make a matrix of dynamic size of doubles, call it A. It's going to have some vector of n by n, which we're going to basically recasting a vector of doubles using the map. We're going to give A an identity along the centers. That means that all the diagonal elements are ones all the way down. And then we're going to update this with deltas in the correct positions for this example. So the first one needs to be -1. And then, so that's here, that's the diagonal element. And then we're going to add off diagonal pieces and then pieces offset. So we're going to add a second negative. So it's -2 here. And then all the off diagonal pieces are given deltas above and below central vector. Okay, we then have some initial Tn condition. We're going to set to 0 and give half of it value, and then we're going to run it. Okay, and that's the initial conditions, and it's going to be solved. You can see that code in the example. So there is then additionally an implicit version of this which changes around the logic, and finally there's a sparse version of this that asks you to push back and do stuff. So what I want you guys to do, I think most importantly, there is a nice video that comes with this if it works correctly. So let me just show what this example looks like. Right, so you see you have the explicit, implicit, and you have a sparse version of these. And it's going to produce some explicit sim.txt. And it's giving you a lot of the code here. I don't think you have to make any edits to this, but the main thing is I want you to kind of get used to read through the syntax of both the explicit and the implicit one. And then if we look at sparse, it's going to give you some things, but it's not going to give you everything. I think I should not have been showing you that, and you should be doing that by yourselves. But the point is that you have to fill in the final sparse one and try it out. There is also that comes with this, I did want to show you, they moved generator for Python. You will need to have NumPy and matplotlib/pyplot. If you're on ARCHER2, you might need to download the results in order to get this to work, because I don't think these are installed in the default version of Python on the system, because it's not set up for this type of visualization, and you might end up with issues with forwarding your terminal, because this will produce a little pyplot GUI that runs the video. But this can animate the solution to the system and watch it equilibrate as you run it, do the solving. I will show you an example of that once you're done, but I think what we should do now is spend 20 minutes or so, so spend half an hour looking at this till I think when we planned our next coffee break, and then I will go through what I think the solutions are at about 3:15. Any questions on that section of the eigen discussion or anything I've shown there? Try to spend a little bit more time on this because I think this, if you're looking at writing numerical codes, then some of the functions of eigen could be quite useful and you may not see in the standard library. Okay, I'll be around till 3 o'clock to answer questions, and then we'll take a short 15-minute break at 3 o'clock to have coffee. Please try this exercise and basically run each of them and try to understand what eigen is doing and how it's doing it for each of the cases. I'll leave this implicit diffusion example up. If I can freeze my screen, which is what I'm hoping to do. Screen so that it only shows this. And send any questions you have in the chat. Please let me know if you have any questions as you're trying to go through those 3 examples of using eigen for the explicit, implicit, sparse run of a solver of the diffusion equation. I will show you what the output looks like in a little video just after the coffee break. But by all means, send any additional questions you have in, and I will answer them during the time. Okay. Keep having a go at looking at these 3 examples. And we will take a break for 15 to 20 minutes now. We will return back at, let's say, 3:20, because it's getting late on day 2, and I'm sure everyone has solved enough C++. Okay, Sophia, I'll help you with that in a second. Can you send which compiler you are using? If you're on ARCHER2, can you do module load GCC 11.2.0? And that has been working for me. If you're running locally, it's only okay. Okay, let me try that in a second. It was working for me yesterday evening, so I'm unsure what's happening. I'll help Sophia with that, but there for everyone else, please take a break and we'll keep looking at this and we will return at 3:20. Okay, are people ready to continue? Okay, so this exercise was kind of a little bit less of an exercise and more of a compiler and codes. There shouldn't have been too much to edit or fiddle around with. It's more to get you used to with some of the things you can do with eigen. The 3 different models here to run. So yes, you could do module load eigen. The idea of getting you guys to download the Git lab instance of eigen was so that you got used to copying your own libraries to include in yourselves and just go through that step. What you should have seen from running this, so if I just run implicit, is your setup matrix looks something like this. And if we compare this to, the example that we had, where delta is 0.4, you have what you kind of expect from setting delta to a value in this matrix. And what we do is iterate through and produce the some output at the end. Now, what I've got is I've downloaded that example output, because when this runs at every iteration, it produces something in implicit sim.txt. Okay, and it gives you the starting point and the iterations all the way down to the 200 iterations. Okay, and the final one was printed here. Before I show that, I'm just going to run the sparse example because it gives you a slightly different output. And in the sparse case, what you end up with is you're passing all these pairs into the system based on location. And this gives you the non-zero entries, and then you get a similar type setup. It's slightly different in this case. I run the output from the implicit example. Let me just wait for this to go through. To try and do it quickly because it's on the wrong screen. It's doing something like this. And it's slowly, we'll just watch a couple of cycles of this. As it's iterating, it's solving the equations, and it's understanding, it's reaching some equilibrium state based on the initial conditions as it converges iteration by iteration. And all the code there to make this little plot with matplotlib and numpy is in GitHub if you're interested to do it yourself, if you didn't get a chance now. Conversion. And you've got some initial conditions where the first half is just 1, the second half is all 0, and then it's starting to iterate from there. Okay. So that should have given you an overview of using a maths library that's not the standard library in the Eigen setup, and some of the useful functions that Eigen itself has, how to sort of look, how they can be combined to be used in some form of interesting program to solve some form of numerical problem. Yes, so moving that, let me just get my demo set up for this section. We're now going to look at threads. Okay, so so what we'll do is we'll talk about threads. There is an example that we can go through, but I'm aware that we've spent 2 days solidly speaking through endless C++, and people may be at the end of their levels of concentration. So I will give some examples as I go and talk through some of the examples in the slides and show you the code compiled and what it runs and does. And then there is an example at the end on the Mandelbrot set that you can look at. But I'm not going to hold people to wait until the end of the course to go through that. You can stay if you wish to, or not. Right. We're going to discuss a little bit of introduction on threads, talk about creating and joining threads in C++, passing arguments to threads, and some bits on synchronization. Going to be our main topics. In C++ 11 threads, there's an API for multi-threading programming built into the C++ 11 standard. It has similar functionality to the POSIX threads, but with an object-oriented wrapper. Sorry, interface is what I'm trying to say. It's based quite heavily on the Boost thread library. It's portable. But it depends on C++ 11 support. So when compilation, you'll have to do -- standard C++ 11 in there to make sure it compiles correctly. Threads are treated as C++ objects. Call a constructor to create a thread. So the construction creates the thread object. Okay. And then synchronization can be handled using mutex blocks, condition variables, or atomics. Okay. And then you have the concept of tasks, and you can have tasks via asynchronous calls, futures, promises, and things like this. We're not going to go into those in too much detail. This is just kind of a high-level overview. Yeah, so threads are objects for the standard of the standard threads class. Those are created by calling the constructor of this class. You can pass an argument for what we want the thread to execute. So this can be a function pointer, a function object, or a functor, or a lambda expression to be passed to a particular thread. That says you're going to then go do a thing. Right? You cannot copy a thread. you probably wouldn't want to either, because that might be, its state may depend on what is executed so far, and would you capture all the information of the things that it's done and left behind? Probably not, if it's acting on other objects. So again, another use case for a lambda expression, if you've only got a small thing you want to do in parallel on multiple threads, and if you want to use a capture to take in information from the current local state without writing your own explicit class for it. So you then can also join threads together, calling join. So this would happen later, and the calling thread will be told to wait for the thread object to finish executing its function or lambda, and then it will join into the main thread. Okay. You need to do this to make sure you concatenate all your threads together at the end of your program, or you'll leave something sort of hanging in effect. Okay, so the hello world sort of function pointer example, we have got a slightly different example here, but that's fine. So you have include thread. We're going to do IO stream of vectors. We have done this before. We have a hello function, and it's just going to print out hello from thread, and it's going to give a thread ID. Okay, so it's going to say get from this thread that I'm currently a part of, and then get its ID, and then end the print statement. We have a vector that's going to be a vector of threads that we're setting up. And remember, the thread is created on construction. We are pushing back. So we're going to create a number of threads in this for loop, and we're going to push back each thread onto this vector. So we've got reference to them. We can keep hold of the thread objects and do something with them later. And then the constructor for thread is taking hello, the function, as an argument. Okay, taking a function pointer. It's then going to call this function pointer in threads in the constructor as it's being run. Sometime later, we are then going to call all the threads to join. We're going to go through the list of threads and call each of them to join together. Okay. That's the way to do this with a function pointer. We can also look at doing this with a lambda function. So in this case, the lambda function is very simple, but we're taking so the same structure, right? We have a main function, we have a vector of threads, we have a for loop that we're pushing back on, using to push back threads onto the vector as they are made when we call the constructor to the class thread. The lambda function has no captures and no arguments. Yes, you can definitely get erase conditions. Of course you can. It's horrible. That's what we're going to discuss in a second about how to try and avoid that. And that's kind of going to be the main learning outcome of this. So this is relatively safe, right? Because all you're saying is go each thread, go away and print. That's okay. Tell your right ID and print. In this particular lambda, it just has a function body. It has no return. But most importantly, again, we've not called the parentheses to execute this lambda straight away. That's going to be called by the thread class at its right time. And then we close off this for loop, and sometime later we run join. Okay. I have an example here, which is that exact example. Yes, it's that exact example I've just shown there. So now the difference here is that I need to add an extra flag to tell the compiler to build this, and that's -p thread. Okay, otherwise it won't compile. And if I try, let's do this again. Something complaining, lots and lots of reference p threads create, not found, right? Run this, and I get it printed out from each thread, its thread ID, and I get a hello message from each one. Okay, so that's kind of a simple use case. We're just calling a lambda. Once the lambda's over, that's it, done. But it creates each thread, and later it's going to join them all back together. So the thread IDs, you can get a get ID on each thread using the standard this thread, the get ID, to call it on the executing thread. So you're calling it on the thread that is run on, returns an arbitrary identifier. It's not much use. If we want sequentially numbered threads, need to pass a number as an argument to the thread constructor. Okay, so you're not going to get some nice naming convention unless you pass it. But again, the details of this are going to be documented on the C++ reference because it's got the standard library. Look up the details of how to get nice threads from there. You can also pass arguments to threads. I have an example for this. But the point of this is saying that you can pass the integer x and the integer y to, in this case, we're only generating a single thread in the main function. It's called my_thread. It takes the function hello, and the rest of the arguments are what's going to be passed into the function hello. It allows you to do argument passing into threads from outside, allowing further control. So you can see this is quite nice. It means that you haven't got some annoying hierarchy, and you don't. And what it allows the thread class to do is decide when it starts to execute the function once it set everything it needs to up. Otherwise, if you called it here, then it would start executing. You can also pass references to threads. So we need to pass a reference wrapper to avoid the argument to the thread constructor making a copy. You can't just do this with the SFM. You need to explicitly call standard ref. And this allows us to do things like incrementing. You have an example of this. Yeah, so I have this example. Yeah, so I think I've made this a little bit more. So we've got x, and we're going to increment it with hello. It's not 10 here. I should have updated my comment. I've duplicated this. So this means that my thread calls hello and then joins back. And I'm going to call my other thread hello on the same reference and then joins back. And then I'm going to print x. If we run this, again, I have to compile with the -p threads to get this to work. I get back 11 because I've incremented twice. Each thread has done an increment. I could put this in a for loop like we had before and incremented multiple times. But the fact that you've got a reference means at the end of the body of the function, the threads have acted on a member of the overall scope of main, not just the updated something that exists in the scope of the function hello. This is quite useful, but you do need to include this standard ref call to the arguments that are being passed in to hello. Right, synchronization. Okay, this is the going to cause pain example that we were just wondering about. So we have some class called wallet, and in wallet we have a private. So because it's a class, everything's default private before we say public. Integer and money. Default it to 0. And then we have some public constructor, which does nothing because we got some default value for money. But then we can also call a function called add money. This allows us to increment our total amount of money in our wallet. So if we, exactly as has been pointed out, if we have two threads called add money on the same wallet object, then we have a race condition. This is where you are competing to do an update, and if both threads at the same time try and grab the resource, whoever gets there first wins, does the update, and the other one may update an older version and then come in later, and that places that back in the location where it's being stored, and therefore then going to overwrite one another, and you have some form of corrupt value, and you do not get both lots of money put into the wallet, you only get one of them. Okay, and this is a really important thing to consider when you're playing around with threads. Threads can be very powerful for improving performance if you can find parallelism in your program and divide up. However, if you can't, if you are not careful with synchronization, you just get horrendous errors. While we're only covering this briefly at the end of this course about how C++ deals with this, for a longer discussion, a dedicated discussion and course on threading and more specifically OpenMP, we run an OpenMP course at least once a year, like we do at MPI, on this, how MPI deals with threading, how OpenMP deals with threads, and how you can use a directive-based approach to thread for loops, and for example, when programming. So this is quite a nice introduction to threads, but for more detail on the topic and the issues with synchronization and how things scale and things like that, that course is something you might be interested in signing up to in addition. Okay, so we talked about synchronization. We've got synchronization as an issue. It can be a concern if we're unable to synchronize threads in some way, but more importantly, synchronize access on an object or some resource. Okay, so we can do this with the mutex lock. Right, so we can call a mutex to protect updates to shared variables. It's natural to declare a mutex inside an object whose data needs protecting. So you're basically saying, in add money, once a thread gets here, I'm locking now, and no one else is allowed to access until I'm done, until the thread I've currently been locked by is finished. And then I'm going to unlock, and then another thread can come along and do an update. Okay. However, we need to be careful to make sure that we do lock and unlock in pairs. Can anyone think of a methodology that might be better, or a way that you might organize this slightly better, so you're not calling mutex lock and mutex unlock, and you want something that's automatically going to do an unlock for you, for the programmer? Any suggestions in chat? Yeah, I mean, yeah. When the function is there, exactly. Something about when the function goes out of scope, exactly, yes. So, for example, we could write a class that wraps mutex so that when it sets the mutex lock on construction and unlocks it on when the destructor is called at the end of the scope. Okay, and that's a lot guard, and we'll come on to that in a second. But just first, we'll look at this example. So here I have an implementation of, or I should have mentioned, you need to include mutex as a library and include thread for threads in these examples to get the functionality you want. We have this wallet class. I've got some standard mutex member here. I've got my add money functionality, which is just doing exactly what I did in the example. I'm going to add to the wallet's money member based on what I input, the function argument money. I've also added, just so I can print the state out, a get money, which is going to const get money value out, so that we can just see and print it out to the screen when we're done. And then the main function here, I've got some wallet. I've got a vector standard threads like we've seen before. And I'm going to do basically the for loop we saw before at the beginning from the first example. I'm going to print out the values of each of the amounts of money that are going to be required. Sorry, are going to be added into the wallet. I'm going to give this operation to each to a separate thread. I'm going to push this back on. I am then, to access the member variable, I'm going to need to take the reference to the member function add money and pass the, by reference, the wallet itself, W. The final argument is I, the amount of money we're adding. So this is a little bit extra, but it's just to get this example to work. I don't really want you to worry too much about this. And then finally, I'm going to join all the threads back together, and I'm going to print out the amount of money we've got at the end. Okay. So I can just run test, and quite obviously I'm adding 0, 1, 2, 3, 4 bits of money into the wallet, and finally the wallet has 10 monies in the whatever your monies are in the wallet at the end. But the mutex has meant that it's protected. Now I could try and run this without mutex and watch it fail, but that's, I'm pretty sure that something's going to save you. Yeah, you have to use the standard reference instead of just a reference, because the thread has its own memory space, and you need to pass it in. I think this is fixed. I read some discussion yesterday when prepping for this where there are some changes in later versions that maybe address this, but as of C++ 11, this is the way to go about this. Okay. So you can see what we're doing here is that this means that as each thread comes in and tries to run add money, it's checking whether the mutex is locked. If it's not, it's going to wait now until I'm able to unlock, and it's going to keep probing, going, are you ready? Are you available? Are you available? Until it's able to catch the unlocked mutex, lock it itself, do its update, and then the next, and then unlock afterwards. Okay. This type of thing is really important, but you can see you can build in this protection into your objects by adding mutex into each object so that its members are updated fairly. And not overwritten. Not fairly, not overwritten. That's what I'm trying to say. Okay, so we need to make sure that the mutex is always unlocked. Otherwise, you're going to lock the memory resource, which is associated with that data member of the class, and never release it. And then no one's going to be able to touch it apart from the thread. And if that thread then ends up closing, then it's never going to be unlocked. So it can be tricky to know when to do this with complex control flows or with some exception handling. And as I was kind of hinting at, it would be better if we had some class that implements resource allocation is initialization. The locking of this is a resource. Okay, so applying this lock is, so we can have standard lock guard, the standard lock guard class as a pattern for controlling mutex. The constructor takes as an argument the mutex or a mutex, which is then locked on the construction of the lock guard, and then the destructor unlocks the mutex when you get out of scope. Okay, and this looks like this instead. So I just have one line now instead of two before, and again I have a mutex member function to my wallet class, and my lock guard takes the type mutex and then creates. So we're just going to call this lock guard, but it's a bit unhelpfully repetition there in terms of what the type is and the name of the particular object. And it takes in as an argument the mutex which is associated with this object. Now, the mutex unlocks when the lock guard goes out of scope, okay, which means that I don't have to have a separate unlock statement, and it protects the programmer from making the mistake of not unlocking. Kind of like when we discussed before about the use of pointers. If I make a new, I have to have a delete. If I forget to do the delete, then that memory is going to hang around, or it's not going to be cleaned up correctly. So this is much better in terms of code cleanliness. Right, can I have an example of this? I think it's just going to do the same thing. So, okay. I will run this for completeness, but it's doing exactly the same thing. It's the same piece of code as I had before, with the example where I have an additional function get money, and instead I've replaced the mutex lock and unlock with the lock guard around mutex. At the beginning of the add money function, I call the same thing. I do the same updates. The way I interact with this from the thread pushback is the same, and then I join, and then I print out the amount of money left. And just to prove that that is still doing the same thing, there you go. But in terms of it just gives you much more protection about making sure that you've closed the mutex. So unlock mutex at the end of the scope. Okay. Additionally, C++ provides an atomic template class standard atomic. It's an efficient lock-free set of operations supported for specializations to basic integer, Boolean, and character types. And additionally, floating point support is in C++ 20 standard only. And what this says is that for certain atomic operations, you don't need to guard at all, because the operation itself is going to protect the update. Okay, but we need to include atomic here to do this. So, but there's only a subset of functionality that will do this and protect you in this way. So you don't assume that this is the case. Kind of make sure you check running right. Here, in this example, I've completely removed any notion. I should actually remove the mutex because it's not needed. I've kept it in there because of laziness. But the point is that there's no need for this, because we've got an atomic that we're calling to update, that every single thread is going to lock the resource as it does the atomic operation, basically. And therefore, I can run this particular update without worry of anything going wrong. If I test this, I can see I'm also doing the same addition. I probably have to get something quite large number of a loop to be able to see it's going out of order, though sometimes it happens pretty quickly. But in this case, it's happening quite nicely. These are more demonstration examples opposed to things I expect to seriously go wrong. But these are a set of ways in which you can either lock or use atomics to protect your updates to shared variables using in C++, using the standard template library. Okay. So thread safe class design, possible to add a mutex data member to the class and make every member function that accesses any mutable state acquire and release the mutex using a lock guard ideally. It's a good design in the sense that multi-threaded code can use the class without worrying about synchronization, so that you're then free to use the class members. However, it can result in unacceptable overheads because it's going to have to do lots of locking and unlocking and do synchronization when it's not needed. So to have correct code, you could introduce a lot of these into all your objects, but to have efficient code, you may want to start removing them, and you just need to be very careful about the use cases in given applications and whether you are in a safe situation to start removing that level of protection. As I said, the semantics and the detail of this is a whole subject on its own. I think the main thing I wanted to get across in this lecture is that there is functionality available in C++ for this in the standard template library, but be careful because you can get into quite horrible bugs when synchronization if you have synchronization issues and things happening simultaneously, updating shared members, it's very difficult to work out what's going wrong. Okay, that's everything for this lecture to kind of finish us off. There is a Mandelbrot set example for you to go through and look at in the exercises. But I'm also wary that people may be quite tired, given the fact it's 4 o'clock on day 2, and we've spent 8 sessions over the last 2 days going through various pieces of the standard template library and covered quite a breadth of topics. I think the main sort of thing I say to take away from this is that the examples will remain available to you via the link that you've used. They'll be up on GitHub. No plans to take them down. I'll keep them more private anyway, so you can go back and look at them and try them again. And the slides will be there also. There is a branch on the GitHub called Solutions. So if you want to go back and look yourselves, you can do. If there's anything you didn't understand or you didn't catch when I went through it, this session will be recorded and will be put up on the link on the ARCHER2 training webpage, so and probably uploaded to the YouTube channel as well, so that if you want to come back later and review what we discussed over the particular section you want to review, you can. Additionally, please send in, I'm sure Claire will email you around about feedback for this. Thank you all for saying and providing any feedback you can is more than welcome, good and bad. We want to improve this so it's useful for the community and that people come along and get value from it. So if there's things we could change or we could add in, that'd be great. My ability to spell might be one thing I can improve on. But please let us know via that channel. And thank you all for staying to the end. It's great that the 20 plus people are here until sort of the end of day 2. That's not always the case. So hopefully you found this useful. I will be around now to answer any questions for another half an hour if anyone has any additional things they want to ask. You can always contact me via email. I think you've been CC'd into my email related to this material. If not, you can find me on the EPCC website if you need to, and I'm happy to answer questions you might have about the content too. The Mandelbrot set examples there for you to try if you're so inclined. But yeah, so thank you very much for attending, and I hope it was useful. And I will be hanging around here for a little bit if you have any further questions.